Okay, so this is going to be our last video with doing some simulation, and this is going to be a transient response. And you can see we have some inductors here, and you might say, well, we didn't do any simulations with capacitors in this demo, and you're right, we didn't. But you're going to do some in your work, and you're going to be able to see the effects of some capacitors on circuits and how they can be beneficial. In fact, we're going to use this circuit that we're looking at here and have a small modification to it. Just so you know, the assignments I'm going to be posting, I'm going to be hand drawing the circuits for this week's, just because it's easier for me and quicker to hand draw than to type them out like you've seen them before. I suppose I could build them in Cadence. We'll see what I feel like doing. And so either way, the circuits you might simulate, they'll be in your assignment here, and maybe they'll be hand-drawn, or maybe I'll just copy and paste the ones from the circuit simulator so they're easier to read. All right, so what do we got going on here? Well, first off, we have two inductors, which are actually very large inductors, 1,000 millihenry, 10 millihenry, and then we have this K of 0.99. That means these two inductors are coupled together. Now, one thing that you won't always see in these diagrams here, I'm going to include it here, and I'm not going to go over much detail on it, but there is something that's important. It's called a dot convention for transformers and for inductors that are coupled. And without going into all that means, when you place the component in Cadence, you'll see there's a dot. And so I'll just show here that the way we're going to be doing the dots is having both dots at the top. We're not going to go into any more detail to it. Now let's talk a little bit about some of these things that we have here in the circuit diagram. This right here, this resistor, I circled the whole, including the ground there, so let me just circle the resistor. This resistor is for simulation purposes only. It's kind of weird. Sometimes in order to get simulations to run properly, you have to do some kind of funky things like this. And when we've done simulations with transformers in the past, if you connect ground without this 100 mega ohm resistor, basically it's basically saying you're shorting your inductors to ground often, and it doesn't like that for simulation purposes. So a cheat to get around that is you put just a giant resistor here, and so you're not shorting those inductors to ground, but they're still connected to ground. They're just connected to ground through this big resistor. Now it seems like a cheat, and it doesn't necessarily make sense why you do it, but again, these simulators are number crunchers, and so the way these models are set up sometimes, and they're simulating lots of big systems of equations and everything else like that, that you can get issues with numbers that just end up not converging or not making sense, and so the simulator doesn't like it. Now, the other thing you might say, it's like, well, wait, I've got two really small resistors here at the top here. This 0.1 Henry and this 0.1 Henry here. This is actually to kind of somewhat model that inductors actually do have resistance. In fact, a 1,000 millihenry inductor probably has more resistance than 0.1 ohms because it's just a wire. And you might say, well, a wire has zero resistance. Yeah, but it's a lot of wire. And wires do actually have resistance. It's just it's so small, we usually ignore it. And 0.1 ohms, of course, compared to like 1 kilo ohm is so small. So you may say again, well, why do I bother doing that? It's again for simulation purposes, and it will be kind of more necessary when we start adding some other circuit components in here in order for the circuit to simulate properly. All right, so let's get back to actually doing the simulation and building it. So for this one, we actually only need the analog library, the source library, and the capsim library. For the homework, you'll also need that diode library because remember, we're going to be doing some diode simulations as well. All right, so let us go ahead and build this circuit here. So first off, let us add the inductors. And you can see, as I'm trying to place that inductor, you can see there's that little, it looks like not really necessarily like a dot, but you can see it's at the top there. And so I want to place both of my inductors with that at the top. And then I've got 3 resistors, actually 4 resistors. So I had a resistor here, and a resistor here, and then one that was over here. And then I have my ground. And now we should notice here, this is actually not a DC power supply, and it's even got this little kind of curly in here, and this is trying to be approximately a sine wave of some sort. Sometimes they don't look very much like sine waves, but this is an AC power supply. So we're not using our DC battery. Now, we have to be careful though. So if you go to your sources, and you say, okay, well, let's just go to voltage. Oh, look, there's this AC voltage here. Oh, I just want to apply that. Wrong. That AC voltage is really used for frequency analysis. And we're not doing any kind of frequency analysis. We are actually trying to still do time domain. So that VAC is not the one we want to do. In fact, what we want to do is, well, what I said is it looks like a sine wave. There's this V sine. That's what you always want to use for like any kind of what I'd say is a wall power or any kind of signal that's a sine wave or what we are going to use typically for AC signals. Now, that's not to say you would never use VAC. If we ever do a frequency simulation in this course, which I don't think we will, but if we were to ever do that, we would use this VAC. You'll definitely do frequency simulations later on in your curriculum here at Tech. So let's do the V sine. So I'm going to add that there. And now I have a lot of parameters I have to set here as well. So before I even connect everything up, let's go ahead and do this. Now, this V offset, it didn't say anything about that. Unless otherwise specified, that V offset's always 0. The offset is basically referring to a voltage offset. And a normal sine wave is symmetric between the x-axis, meaning, well, it's not symmetric about the x-axis. What I should be saying is that it, the center kind of thing, it goes up to 120 and down to 120, up to 120. So, you know, there's no, it's centered. That's the word I'm looking. It's centered on the x-axis. Now, it did tell me the amplitude was 120 volts. And I'm just going to drag that a little bit over here so it doesn't there. Frequency was 60 hertz, so it's just 60 because we're kind of simulating wall power. Now this AC, I forget, honestly, it's been so long since I've done some of this stuff, I forget what that is, but I always just set it at 1. It does need a value. Setting it at 1 simulates it just fine. So let's go ahead and connect everything up here. Like we have in the circuit diagram. And I know I still have some values I have to change. And then this is 1,000 millihenries, which, you know, with the way I've been saying, doing notations, engineering, that's really, instead of 1,000 millihenry, maybe I should have written it as 1 Henry. But that's fine, just as 1,000. And then this was 10 milli. And then these were both 0.1 ohms. Now, whoops, this here was 100 meg. Now this is what's interesting about the simulator. If you do 100 capital M, it won't work for you. It'll say, I don't recognize capital M. And for some reason, the simulator wants us to actually write out meg. So 100 meg, M-E-G, capital M-E-G. I don't think it needs to be capitalized, but you actually need to put the meg down, and that's mega ohms now. All right, now it looks like we might be ready to simulate, but we actually have something missing. There's this K is 0.99 in the circuit. There's no circuit element to that, but there's this K equals 0.99. So I need to get that in here somehow, and I don't want to just put it as a text box. It's got to somehow be associated with the inductors. And so actually, if you go to analog, your analog library, and you scroll down, there's this K linear. And that's what it is referring to. It's just that K we need. So if I double click on it, you can even see the word coupling. And if I just put it here, actually it doesn't matter where you put it. I could really, oops. It could sit over here and it wouldn't matter. So it has this, the position of this is completely irrelevant, but I like to just kind of put it by the inductors that I'm coupling. And we said 0.99. And the reason I like to do 0.99 is sometimes simulation doesn't work if it's 1, and the reality is 1 is ideal, and technically you never have 1. Now, the other thing we have to do, though, so we're not quite done, is we have to tell this K what inductors are coupled together. Because right now, these inductors, the simulation is going to treat them as if they were magnetically isolated. That they were like, even though they're close in the picture, the simulation is going to treat them as if they were far away or if they were shielded. Okay, so we have to tell them that no, these aren't shielded, that these two inductors are coupled together. So to do that, you right-click on the K thing here once it's been selected. Because if you just right-click on the K without selecting it, it doesn't work. So right-click on, first select it and it turns pink, right-click on it, then edit properties. Now yours might not look like this. Yours might look like this. I don't like this view. This view, you have to kind of scroll across for everything. So and you might have seen what I clicked, there's this thing that's called pivot, and basically it just exchanges the rows for columns and columns for rows. And so I like doing it. And you can actually even see coupling here. You could change the value of the coupling coefficient right here. But now you see these L1, 2, 3, 4, 5, 6. So here is where you tell it what inductors are coupled. Now, I want to emphasize, I'm going to be putting L1 in here for this and L2 in for this. That has nothing to do with these names here. You need to look at what are the names in your circuit diagram. Well, one inductor here is L1, the other inductor is L2. So that is why in the properties here, I do L1, and then I'm going to go down and do L2. And you might say, what do you do for L3, 4, 5, and 6? You leave them blank. The reality is you could have more inductors coupled together. Now I'm just going to close this tab out, and now my circuit is ready to simulate. So I'm going to do a new simulation profile, and this is still a transient one. So create. And then this is my transient response here. Now, this is where we have the other outcome that we said we need to have learned by the end of this week, is right now the runtime for this is 1,000 nanoseconds. And if you were to run this, you would see nothing on the output once you put probes down. It wouldn't look interesting at all. And the reason is we have to think about this for a second. The frequency of this sine wave is 60 hertz. Now, frequency is equal to 1 over the period. Or you can think of it as the period of the signal is 1 over the frequency. And capital T is used for period, and then lowercase f for frequency. So that's very important to know. Whenever you have an AC signal, you should always be using that equation I started. Whenever you have an AC signal. So let's pull up a calculator here. And I actually had already done some of the calculations there. So I have a 60 hertz signal. So 1 divided by 60 hertz gets me a period of 0.016 repeating forever seconds. And yeah, if we went in engineering, That'd be 16.67 milliseconds. Well, that would be one period. I often want to see more than one period of a waveform. And so I'm going to just go ahead and multiply this by 4, saying I want 4 periods. And so I have 666 milliseconds, 6666 going on forever. I'm sorry, not 606, 0.066, which is 66 milliseconds going on forever. And so I was going to say, okay, well, if I want to then show 4 periods, I'm just going to round that up to 0.07. So I'm going to say that I want my runtime to be equal to 0.07 seconds, or 70 milliseconds. You want to always have at least 4 or 5 periods displayed here. So it's only running for 1,000 nanoseconds, which is 1 millisecond. So it's running for 1 millisecond, and we just computed that I need to run this for 70 milliseconds. Now the start saving data after seconds, this is for if it takes a certain amount of time for the circuit to charge up. You might want to wait maybe 100 milliseconds before you actually start recording data. But for now, we don't have to worry about any of that with the circuits we are doing. Now, we do want to set this maximum step size because by default, Cadence doesn't do very many points to simulate because it takes more time to simulate when you do more points. But it doesn't, you don't get nice smooth graphs here. So what I'm going to do here is I like to just say, okay, well, if I were to divide that by, if roughly 100, that'd be like roughly 0.1 milliseconds, but I want to do a little bit more. So I'm going to do 0.01 milliseconds, which, yeah, I know that would be 10 microseconds, but I'm just going to do 0.01 milliseconds. I'm going to hit OK. And so I'm going to go ahead and simulate this without having any probes on first. So it simulates just fine, but there's nothing here, and we can see 0 to 70 milliseconds. Now the first thing I'm going to do is I'm just going to go ahead and put a voltage probe on the source here. And let me thicken this line up. I really need to figure out how to change that default there. And we can see, oh, yep, it's a sine wave, nice pretty sine wave, and we can see we have 1, 2, 3, I'm sorry, 1 period, 2 periods, 3 periods, 4 periods, and a little bit. All right, and it goes up to 120 volts, down to minus 120. Great. I want to show you some things here as far as, now that we have this AC signal here, I want to show you a couple things that we can do as far as measurements. But I'm going to go back here, and to do these measurements, I'm going to first do some other things here. I'm going to do what's called a net alias. I don't think we talked about this before. It's this right here called the net alias, and it's for N. I'm going to put net alias, and I'm going to say input, and I'm going to just put it right there. And I'm going to put another one here, and I'm going to put this here, and I'm going to change this one to named output. And you don't have to do this, but it makes it easier to do measurements. Like when I say measurements, have the system do measurements for us. So we go back here. Yeah, it's the same graph. I'll thicken the trace property up here again. All right. So if I go to trace and then evaluate measurements, I'm going to turn off for now currents and power because I'm just going to look at voltage. But you can see here there's this output and then there's this input. But what I could do is I could say, what is the maximum of the input? I'm going to click OK, and then it puts it down here in this measurement. It's 120 volts. Oh, well, I could add another measurement. Maybe I want to know what the minimum of the output is. And I said the output. Minimum of the output is minus 11, which makes sense. I meant to really do the minimum of the input, but that's okay. I'll do that one next here. Let's look at the minimum of the input. minus 120, which makes sense. Input goes up to 120, down to negative 120. And so that's my input. The other thing you can do here, as far as a measurement, is we can say evaluate measurement. And if I want to evaluate the frequency, we can see, wait, there's no frequency here. But if I scroll down, I scrolled down too far. There is a period here. You can measure the period. And we just said that frequency is 1 divided by it. So I can actually put a equation here. I can do 1 divided by, and I'm going to say period of the input. And we get 60, which again, not surprising, it's 60 hertz, right? Well, we could do the same thing here. And you can see as you start putting more measurements in here, you kind of start getting where you have to scroll down here. I could also then do the same thing here and say, well, what's the period of the output? We haven't even looked at it, but I can still do 1 divided by the period of the output. And we can see that the output's also 60 hertz. Okay, well that's great. Let's actually look at what the output is here. So I'm going to now place a voltage marker just on the output. And going to increase the thickness of this here. And so we have here what the output is. And we can see it's a sine wave still, goes up and down. It's got the same period frequency as the input, but it's got a much lower maximum voltage and minimum voltage. In fact, we already did the minimum voltage. It goes down to basically minus 12 volts. So really what this is doing is this is called a transformer. It's called a step-down transformer. I'm stepping down from 120 volts down to 12 volts essentially. And so you know this is actually the first step of a very basic DC power supply. The first step if you're trying to make a DC power supply out of wall power is you don't want to start, like if you're trying to make 5 volts, you don't want to start with 120 volts. You want to first step that voltage down. So I'm going to step that voltage down. I'm going to step it down, and in this case we stepped it down to 12 volts. And then from this 12 volts, I might convert it to a 5 volt signal. And it's still AC, and as I said, we're going to want to try and convert it to a 5 volt DC, which is what we're going to work on this week and next week in your simulations, in your homework. So you can kind of see, and again, you don't need to know the circuit theory, all the details. We have the basic circuit theory of, okay, what a capacitor does, what the diodes do, to have an idea of what's going on in the circuit. We don't have to understand all the precise equations.